Okay, welcome everybody. I think we're going to get started. This is the March 2023 edition of Green Infrastructure, Climate and Cities, a monthly seminar focusing on the unique challenges that climate change poses for Northeast cities and what we can do about it. My name is Franco Montalto. I'm a professor at Drexel, and Drexel is one of the institutions that are part of the Consortium for Climate Risks in the Urban Northeast, a NOAA-funded initiative focusing on this topic. If you're joining us for the first time, this seminar series began back in 2014. All of our previous seminars have been recorded and are archived on the CC Run website. Feel free to watch any of them by going to ccrun.org past seminars. Again, if you're joining us for the first time and you are in need of continuing education credits, we provide continuing education credit certificates to attendees to our seminars. Before I get to today's speaker, I just want to make a quick announcement. CC Run, working with the City of Philadelphia and the Delaware Valley Regional Planning Commission, among others, initiated a few years back a large collaborative effort to develop a climate resilience research agenda for the greater Philadelphia area. And I'm happy to announce that we have a report that will be imminently released. That report also contains CC Run's most updated climate projections for the Philadelphia region. So 2-in-1 climate projections plus a listing of research items that could help promote resilience in the Philadelphia region. And we just ask attendees today if you have any ideas. We're looking for a lot of different avenues for publicizing this report and distributing this report. So if you have a chance, please put if you have any avenues or so institutions or forum that you would recommend us to introduce the report to, please put that in the Q&A and we'll record that. With that, I'm going to move on to our speaker today. So this version of CC Run seminar series is focusing on mitigation and adaptation embedded in the broader climate transition. And our speaker is Corey Lesk, who is a postdoc fellow at Dartmouth. And I'm going to introduce the PI of CC Run from Columbia, Radley Horton, to introduce Corey. So Radley, go right ahead.
Great. Thank you, Franco. Really excited about this talk today. So I first met Corey back in 2015, shortly after he had finished his undergraduate degree at McGill. Corey started working with us at Columbia and sort of by extension at CC Run, really initially working on kind of that last iteration of CMIP models and providing projections for decision makers in the Northeast initially, sort of around 2015 or so. And one thing I was struck by really early on about Corey was his commitment to communicating climate science and really having conversations with people about their vulnerabilities. And, you know, really sort of having that spirit of wanting to make contributions to impacts and resilience thinking. He went on from there to travel really all around the world, working on climate science communication with communities all around the world. Then I was, you know, thrilled and fortunate that he did a PhD in my group at Columbia, where he you know, pushed all of our science along so much, always sort of focused on the impacts that his research could have, and on making Columbia's graduate school and the overall university environment a better place for everybody. So really thrilled to introduce him. As Franco said, he's now at Dartmouth. As I said, he's a climate impact scientist, postdoctoral fellow in the Department of Geography at the Neukom Institute at Dartmouth College. His work, as you'll hear, focuses on the interaction between vegetation and climate and how they affect agriculture and water resources in a warming climate. But he also examines the sustainability and robustness of mitigation and adaptation pathways towards a livable climate future. So really exciting to hear that kind of systems analysis perspective he brings, and more generally, just the kind of holistic, even sort of humanistic lens that Corey applies to his work. So with that, I'm thrilled to have you, Corey, and I'll hand it to you to take it away.
Thanks, Radley. I'm going to stop sharing, and Corey, please feel free to share your screen.
All right, thanks so much for the introduction. I'm going to ask if you can hear me because I don't see my face outline. There it is now. Okay, so you can hear me. Yeah, thanks, Bradley, for the introduction. Thanks to Franco and Nikki for the invitation and setting this all up. Excited to present to you this research, which I'll take you through. But to start with, I want to also acknowledge and thank my co-authors here, which includes Bradley, as well as folks from Canada, people from the United States, United Arab Emirates, the UK, and Germany. So a big international team was behind this, and I led it. So I'll tell you about it. Fossil fuel emissions are back. We are now on the other side of this pandemic, but fossil fuel emissions are very much still here. So this axis is showing you global total CO2 emissions since the 90s. We've been going in the wrong direction. We took a little dip during the pandemic and then bounced right back up in 2021. And now we're even higher than that. And, I struggle to kind of put this picture together with some other thing that I think is happening, which is that the climate transition is really starting to happen in earnest. And you can see this, I think, in the discourse changing. So high profile opinion pieces saying that the green transition is happening fast. Recent legislation is only accelerating that. But also, I think you can see that investment is headed in the right direction. So for instance, in 2015, this is data from the International Energy Agency. In 2015, global total investment in renewables was less than the investment in fossil fuels, which was pushing that curve in the wrong direction. But in 2022, for the first time, investment in renewable energy is now outpacing investment in fossil fuels. So I think there's, despite the fact that our emissions are still very high and need to go in a different direction than they're going, there's actually a transition starting to happen. And the question now is, how fast will this transition be? How robust will it be? And how effective will it be? And when I mention the words climate transition, what usually probably comes to mind is things like this, deploying renewable energy like wind power and big solar farms, but it also includes adaptation. So that might include retreating from coastlines and rebuilding settlements further inland because of the impacts of sea level rise, maybe building coastal protections in other places where it's cost effective or population densities are high enough to merit that, or boosting air conditioning so that we can live with rising heat stress. So we have kind of two pieces of this transition: avoiding climate change by deploying renewables to get off fossil fuels, and then living with the impacts that we have chosen not to avoid, things like this. So I want to just give you a bit more of a background on that. So with a warming planet and warming seas, events like this are more intense and more frequent. Things like coastal storms that flood coastal areas and eventually make it not very appealing to live there anymore, or completely impossible. So we'll likely need to move some of the global population living near coastlines towards further inland places. That requires kind of rebuilding those communities, and this requires materials and energy. Other coastlines may need coastal protection, things like this. This is a seawall or a sea dike, and these are made out of concrete and steel and require energy and materials to build. As we have more heat waves, we will need to have more air conditioning for comfort, but also just for survivability, especially for people in vulnerable health situations, and that takes energy. And then in order to kind of prevent this situation from just getting worse and worse, we need to cap our total CO2 emissions, say for some carbon budget target, like equivalent to 2 degrees of warming maximum, and that it will involve massive renewable energy deployment around the world. So all of these interventions are part of the broader climate transition, and these require energy to do. And currently, we don't have renewables online in huge quantities, so that energy is going to come from primarily fossil fuels. Some of these interventions, like rebuilding settlements, building out coastal protections, use very emissions-intensive materials. And I mean, beyond just the energy it takes to make those materials being satisfied by fossil fuels, just the chemical reactions to make these materials emits CO2 as well. So for instance, in our current breakdown of global emissions, cement and iron and steel contribute around 10% of global emissions. So this, I think, requires a term, and I think a good term for it is embedded transition emissions. And these are just the emissions likely to be produced by the climate transition itself. And I think these embedded transition emissions raise two questions. The first one is just, how big are they? How much CO2 emissions are embedded in this transition? And I want to give you a reason why I think this question is important. So you can conceptualize climate change as this kind of carbon march from our pre-industrial 0 degrees of warming world through to some level of global warming that we want to stop warming at. And we've already emitted so much CO2 into the atmosphere and into the Earth system that now occupies the kind of space between that 0 and that 2. So this is this carbon space. And the space that's not already occupied by our historical emissions is the space available for remaining carbon budget. And this is really our runway to get to a sustainable energy future. So the question really is, how much of this budget will be taken up just by the mitigation and adaptation we need to do to get to a stable situation? And these emissions, or this question, this value, is not really presently accounted for in research or in policy. It's not really in the IPCC reports. So the question is, could embedded emissions compromise the robustness or effectiveness of this transition? And then I think there's a second question that we really need to consider is, how sensitive are these emissions to the pace of the climate transition? And the reason I think this matters is we're kind of at this crossroads now where we have this current policy path, which is relatively low ambition, even though things are starting to change, making this kind of a confusing situation. And maybe we have many barriers along that path that would make it hard to get off that path as we go into the future. So we're at this crossroads. That's one branch we could take, but there's all kinds of other paths in front of us, all the way down to actually meeting our 1.5 degree commitments based from Paris. And this would be a high ambition, well executed transition. And then there's maybe a path in between, maybe 2 degrees. And so there's a wide range of possible transitions in front of us, and maybe there's a wide range of embedded emissions too. And so the pace of our transition will be relevant to those embedded emissions and the scale of this problem. So for the rest of the talk, what I want to do is give you first a sneak peek of our answers to these two questions, because who likes surprises? And then I'll briefly outline the modeling approach and give you a bit of detail, because I think some people in this audience will be interested. And then I want to go through, with that understanding of what these results are based on, a little bit more detail on the results. And then I'll trace some wider implications, recent literature, and open questions, and then open it up for your questions, which I'm really excited to hear. So the first sneak peek is that there are substantial emissions embedded in this climate transition. Under our kind of current policy path, which I'm calling a delayed scenario because it's not a great path, which would get us to 2.7 degrees of warming through 2100, the total emissions are 185 gigatons of CO2. That's equivalent to 5 years of current global CO2 emissions, which is enough to get us halfway to 1.5 degrees of warming just by itself. The second sneak peek is some good news, though. The bulk of these embedded transition emissions can be avoided or minimized through a more rapid transition. So I will take you through these graphs in more detail in a little bit, but just notice that if we move from our delayed path here towards something more like 2 or 1.5, these bars go down, and that's the emissions embedded in that transition. This is for renewable energy deployment. This is for adaptation, but they all go down as we move towards faster transitions. So 80–90% of the problem can be avoided just by doing what we know we need to do anyway. Okay, so now I want to give you a quick trace of the methods. So the basic idea is to sum over time the amount of a mitigation or adaptation intervention, which I'm denoting here with these little subscript i's, times their emissions intensity. Okay, so the total emissions in the transition can just be broken up into the sum across each intervention we're considering of the amount of that intervention times the CO2 emissions per unit of that intervention. This is just kind of breaking down this big problem into smaller pieces. And those I's, those interventions, are renewable energy deployment, coastal protection, coastal retreat, and adaptive space cooling. Now, to get these N's and I's, capital I's here, we need to bring together some models to try to come up with these values. So we have 3 models. These are sectoral models that we use to project these quantities. Let me tell you a little bit about them. The first one is called NetSat. That kind of stands for Sustainable Net Energy Transition Model. And this is what we're using really to model the deployment of renewable energy. In case you're into energy models, this is a backcasting global scale energy model that's just constrained by simulating energy system dynamics to meet remaining carbon budget. And it simulates the energy mix across fossil fuels and various renewables. The inputs it takes in are things like energy return on energy invested across the different energy sources or carriers. And it takes an assumed power per capita, so basically energy per person in the world. But importantly, this model tracks net energy available to society versus energy invested into building and maintaining energy infrastructure. So that's why there's this net word so prominent in the title of the model. And that's really useful for us because it directly simulates the energy used to deploy renewables. So that's the first thing that this model gives us. The second thing it does is give us the energy mix over time, which determines the emissions intensity of each intervention, right? Just because the energy mix is becoming more renewable as we do the transition. The second model is called CM, Coastal Impacts and Adaptation Model. This is just a cost optimization of adaptation decisions model. So it takes as inputs, geophysical and economic data about the coastline, as well as estimates of retreat and protection costs, and some sea level rise projections to just try to cost optimize the correct optimal decision here. And I say correct in a weird tone with scare quotes because, again, all we're considering is the costs that go into the model, which usually neglect a lot of really important human realities. So that's a critique I have of this model, but very useful for many applications here. And this just gives us the amount of coastal protection and retreat over a set adaptation horizon. And finally, the third model of bringing together is the energy demand generator, which is a building energy model. And it takes as inputs demographic and economic projections, which are kind of scaled to building parameters and building efficiencies that kind of match social futures that are projected. And it also takes climate warming inputs to estimate that cooling energy. And this gives us the amount of adapting cooling energy demand. Okay, so these outputs are not directly what we need, right? We need to get to emissions. So we have to complement these outputs with a bunch of offline emissions of factors from literature, so life cycle analysis. I'll just give you a few examples of the kinds of things we need. We need like the materials that go into a sea dike and a relocated settlement. We need the embedded energy in those materials, and then we need the emissions intensity of the energy sources going into those materials, among lots of other things. But basically, once we've done all that, then we can solve this equation and estimate the emissions embedded in the transition. Now, I want to give you a little bit more into all the little kind of quirky modeling projects we need to do to answer this question. So here's just a schematic of a cross section here of our sea dike model that we needed to do in order to kind of get the materials in these things. So I worked with a high school intern who is now an engineering student as an undergrad. And, we just went through coastal protection design specs, documentation, and came up with these kinds of like best practices. So you have to see on this side, we have this kind of fill with soil and rock, and it's covered in a concrete revetment, which has certain shape and a certain thickness, and it also has a foundation. And based on that, we can calculate the reinforcement in the concrete and the concrete. So that was just kind of a fun idea. I think some of you might be interested in. And to just totally scare you here, and you can come back to this if you have detailed methods questions. This is kind of a flow chart of the whole process we needed to get these total transition emissions. And you'll recognize those three models really at the heart of this whole flow. So please ask me about this if you want to know more method stuff. The final piece of methods we need is to answer the second question about the pace of the transition and its influence on embedded emissions. So we have this crossroads, and we simply just sampled three plausible places in this wedge of futures we could be headed into. So we have a delayed scenario, which is actually most consistent with our current policy path. And we have a rapid scenario, which is probably optimistic at this point in time, and a gradual scenario, which is our probably most realistic. And so these two poles here are kind of on the upper end, a kind of low ambition scenario with lots of barriers to really an effective rapid transition. But this implies we'd have more adaptation needed as we have more warming going on, and we have dirty energy to do all of that transition work. On the other end, we would have higher ambition, or actually super high ambition, very well executed, less adaptation will be needed, and we'd have cleaner energy to do it all. And then in the middle, probably what we can hope for at this point. And that's what I want to start with. So I'm going to take you now through the results just for this middle case, the gradual transition, which is headed towards 2 degrees of warming maximum. And then I'll come back to the two others later on. Okay, so this is a simulated deployment of renewable energy from the NetSet model I was telling you about a second ago. It is showing you the historical evolution of primary energy demand on this axis across different carriers. So the purples here are coal, oil, and gas. And we have some kind of biofuels, nuclear and hydro down here, which don't really change that much. The gray line separates historical and then projections. So here is where the model really starts to simulate a transition. And you'll notice that as we go into the late 2020s and 2030s and 40s, that these orange, yellow, and green wedges start to increase. I just want to point out that CSP stands for concentrating solar thermal panel, solar thermal power. That's these big farms of mirrors heating up, sodium in a tower in the middle. So thermal. PV is photovoltaic, so solar panels. And you can see this relatively fast deployment of renewables, pushing those fossil fuels out of the energy mix. Now, crucially, this black dotted line separates net energy available to society, that's below the line, from energy use to build and maintain energy infrastructure. So going into the future, this energy above the dotted line is energy used to deploy those renewables. And you can notice that the beginning phase of that energy investment into deploying renewables comes from fossil fuels. And I just want to take a break and point out that this is actually kind of happening. So a recent example that's been attracting a lot of media attention is Indonesia's huge green industry plan. So there's been massive investments in building kind of green tech industrial plants trying to use and add value to Indonesia's critical natural resources. But since they currently lack hydro capacity to other renewable capacity to power this big industrial park that they're investing in, they're actually needing to bring on coal power plants as a backstop to provide energy to this project. So, not to say that Indonesia is to blame. They're trying to industrialize and they need power to do it. That's what we did, and we caused most of this mess. But just to give a reality check that investment in fossil fuels into deploying renewable transition is actually happening right now. Okay, so all this fossil fuel use to deploy renewable energy results in emissions, and that's what I'm showing here, split out over coal, oil, and gas, but the total is what's really important. That amounts to 95 gigatons of CO2 in total over 2020 to 2100. And if you put that into percentage of the 2-degree carbon budget, that's about 8%. That's, I think, a meaningful slice of the carbon budget. All of these emissions cause warming and sea level rise. So these are the projections of those geophysical changes. On this axis, we have global mean warming represented by cooling degree days. That's a heat metric for representing air conditioning demand. So that goes up and starts to stabilize as this transition is deployed and emissions come down. Sea level rise continues much more kind of linearly. And this sea level rise causes a need for 31,000 kilometers of coastal protection across the global coastline and 67 million people needing to retreat and rebuild settlements inland. I just want to give you a spatial view of where these things are located. So on top here, we have coastal protection represented as a sea dike. You can see the dots where coastal protection is built. So much of the US coastline gets some level of protection in some places, a lot of Europe, a lot of Asia, but critically, not very much of the African coastline. And I think, again, this relates to the undervaluing of hard to quantify human in terms of where adaptation is deployed. You can also see that retreat population is widely distributed around the global coastline, but the colors here are a logarithmic scale. So this dark blue is one equivalent of one person, whereas these greens and yellows are tens to hundreds of thousands of people. So this is going on well distributed around the globe. All of this adaptation leads to emissions. So I'm here showing you for protection, that's under 1 gigaton of CO2, retreat shy of half a gigaton of CO2, and cooling similar in magnitude to retreat through 2100. But importantly, this adaptation y-axis here is much shorter than this axis here for deploying renewables I showed you a second ago. And so the transition emissions, as we've modeled it, are strongly dominated by renewable deployment. In other words, the mitigation side of things is the lion's share of transition emissions compared to adaptation. Now, I'm going to flag that because at the end of the talk, I'm going to show you a recent paper that finds a much larger. I wanted to give you a quick look under the hood at some of the things that are going into this coastal adaptation emissions estimates. So emissions in materials come from both energy and processes. So the energy is making heat that we need to produce concrete and steel, but there's also process emissions. And that's what I'm showing in these pink bars here and this purple bar here. So these are the emissions intensities on the y-axis for sea dikes and for coastal resettlement here. And the purple bar is the purple bars are the energy emissions, are the process emissions, and the pink bars are the energy emissions. And you can see the emissions intensities coming down over time as we go into this projection, because we have built into this simulation improved efficiencies in terms of process emissions coming from chemical reactions. We've also are decarbonizing our energy mix, so those emissions related to energy are coming down over time. So I just wanted to give you a quick glimpse of like some of the detail I'm glossing over in this method, and feel free to ask me about this if this is something you're interested in. But one key point is that, you know, if adaptation is happening kind of in the middle of the transition, it's already drawing on a much cleaner energy mix. Okay, so now I want to come back to these two tail cases, a really high ambition, rapid transition, and a sluggish, delayed kind of path. So I'm going to show you now those simulated transitions for these two cases. So this is a very similar graph to what we had before. Primary energy demand on this axis, over time, historical, gray dotted lines separating from the projections. For our 1 to 1.5 degree world, you can see those purple slices are really steeply pushed out of the mix, replaced by these renewables. In our delayed scenario, those purple slices of fossil fuels are replaced much more slowly as renewables are deployed much more slowly. So fossil fuels stick around through the rest of the century in pretty big share. But importantly, if we draw our attention now to the dotted line, which again is showing you energy investments into building and maintaining energy infrastructure above, you can see that we have a big spike in energy investment into this, that we need to do this really steep, rapid transition, but it quickly becomes dominated by renewables, whereas fossil fuels stick around in the energy mix available to the transition in our delayed scenario. Okay, so let's consider the total emissions here. So what I showed you before is this the gradual scenario, 95 gigatons of CO2. In our delayed case, that's about a doubling, but it's very steeply reduced by about 80% in our rapid transition. And if you go from our current policy path all the way to this really ambitious 1.5 degree path, we get a 90% reduction in emissions from deploying. Now, if we look at emissions, the increase in, emissions from adaptation, the increase in emissions as we go to slower scenarios is super steep. And much of this increase is due to a big increase in cooling energy demand, but it's also because of increases in retreat energy and emissions and protection emissions. Between the 1.5 and 2 degree scenario, there's not that much increase. And you get this really steep increase as we go to the 2 degree. So I want to just explain why this is. So first off, renewables are built with renewable energy in this rapid case. And we have clean power that is rapidly available to supply power for adaptation. Whereas in this delayed response, renewable energy is mainly built using fossil fuels through much of the next 80 years, and that leaves dirty power available for adaptation. And that kind of, so that's kind of what's being shown in this gray bar here. So I want to give you a little bit more of a view of what that gray bar means. So we can split out those increases in adaptation emissions into two components. The light gray bar is related to the emissions intensity, right? So that's the increase in adaptation emissions due to the fact that we have dirtier energy to do adaptation. But there's another component, which is the change in the amount of adaptation that's required. That's the dark gray piece up here, because we're in a warmer world, because there's more emissions, more warming, and more adaptation needed. And interestingly, most of the increase in adaptation emissions under slower transitions is due to dirtier energy supply. And more climate change is the secondary driver of increased adaptation emissions under slower transitions. So this was a bit surprising to me, but I think it also shows just like the power of moving to faster transitions for avoiding this problem. So I want to give you two take homes on this result now, and these are coming back to the sneak peeks I showed you before. Under our delayed transition, we can get up to 185 gigatons of CO2 through 2100. That's a serious amount of emissions. 5 years worth of our current emissions, enough to get us halfway to 1.2. But the good news is that we can, if we increase our ambition and move towards a more rapid transition, we can reduce those embedded emissions by 90%. Okay, so I want to give you a few implications to my mind as we head towards the discussion. The first implication is that total transition emissions, according to how we've modeled it, are dominated by mitigation, deploying renewables. And I think that this makes them hard to avoid, because while there are natural low energy alternatives to putting a bunch of hard infrastructure in place, such as conserving or restoring coastal wetlands that are so effective at protecting coastlines from flooding, but also supporting a vibrant, lively biosphere, we don't have those kinds of alternatives to building out renewable energy. So the energy that it takes to build out renewable energy must initially come from fossil fuels. And that building those renewables just takes a lot of energy, and there's no simple alternative to that, except for using a whole lot less energy. A second implication is that this is a big problem, but it's an avoidable problem. So I showed you this kind of space available for the remaining carbon budget figure to motivate the first question. And I think on our current policy path, just deploying renewables on a current gets us halfway to that 1.5 degrees of warming. So half of our space available in our carbon budget for everything else that we need to do in the economy is taken up just by the transition on this not very desirable, slow transition. But if we deploy fast, we can shrink that slice down to only 5% of 1.5 degrees. And so I think what this means is this is a hidden benefit of rapidly getting off of fossil fuels. And if this is not included in our policies, it means we're undervaluing the benefits of a more rapid transition. And I think this opens up also more carbon space for transition success elsewhere in the economy. A third implication I want to raise is a whole host of equity concern. So one is that wealthy people currently use much more energy. In the United States, we use at least 6,000 watts per person. In the global South, that's more like 2,000 on average, and as little as 1,000 watts per person. So wealthy people have more energy infrastructure to decarbonize. So I think they are more responsible for these embedded emissions that we're simulating in this transition. There's also more coastal protection where capital density is high, according to this cost optimal model that we've been using and that I've been kind of critiquing in the background. So there's less protection in lower income areas, and they bear the brunt of the impacts and have done the least to cause historical emissions. And so I think there's the potential in this transition to worsen this kind of, or further this historical climate inequality. And I think these results bring to attention a new angle of equity that needs to be considered for a just transition. So those are three implications I want to bring your attention to. And now I want to show you a cluster of literature that came out right at the same time as this paper I've been presenting you. So the paper I presented you came out in November. There was a paper a few months before that, and a paper a few months after that. And so this one here is on just the energy side, just the deploying renewable side. They had a whole complementary independent modeling approach and found very similar estimates to ours. So they have found a range of 70 to 395 gigatons of CO2 embedded in deploying renewables, definitely the same order of magnitude as ours. We found something like 100, so right in the middle of the range. This paper used a whole complementary set of methods to estimate adaptation emissions. They found 300 times greater embedded adaptation emissions than us. They found 350 gigatons of CO2 equivalent. Now, this equivalent is key because equivalent means that there are other greenhouse gases they're considering. We only considered CO2, but that is certainly not enough to explain this 300 times greater estimate that they found. So I think this this indicates the kind of big uncertainty that there is in these quantities, and how we kind of need to start putting together an uncertainty estimate and a more robust kind of multi-method estimate of this potentially really important problem. And I just want to point out, if you take the higher range of the estimate of deploying renewables here and of adaptation here, so 400-ish and 350-ish, that's like 750 gigatons of CO2. That's starting to approach the 2-degree remaining carbon budget, which is 1,100 gigatons of CO2. So a large part of the remaining carbon budget might be taken up by just the transition itself, which would be a big problem. So I started off by kind of saying that I think the climate transition is actually just kind of starting right now in earnest. But I think a conclusion here is that, as ever, speed is essential. So thanks so much for your attention. I'm really looking forward to hearing what you think. You can email me here, and I want to give some shout outs to some colleagues who helped figure this out. Delavan built the CM model. Caleb did a master's thesis on this. Anton was my high school intern, and other friends and colleagues.
Thanks so much, Corey. That was great. It was really, really provocative presentation. We got a number of questions here. I'll start posting some of them to you, but as I do, I'm just invite others. If you have questions, please put them in the Q&A. We have plenty of time for discussion. So I'm just going to sort of ask the first question myself, because last month, our presenter was talking about the greenhouse gas emissions embedded in global defense spending. And one of the things that stuck out in my mind is, or that stuck out from that presentation, was that actually those emissions had not been, have not been tabulated, have not been computed in, especially in setting targets, say for the Paris Climate Agreement or others, and simply because they're not tracked, they're not publicly reported. But you mentioned that 8% of the global climate budget, if I got it correctly, could be just the transition, if I understood correctly, just the emissions associated with transitioning. Is that new information, or has that always been something that's been tracked? In other words, was there always this understanding that there would be emissions to change from what we're doing now to what we want to do in the future?
Great question, thanks. I think it's more of a parallel to the military emissions situation. So a lot of this is prospective. So the transition hasn't really reached a big industrial global scale, even though I think it is starting. And so these emissions are really in not the historical accounting of emissions, but are modeling nexus of projecting emissions through the transition and emissions produced by the economy in the future. And so energy investment into energy is in some of these integrated assessment models that are kind of the ordained models for the IPCC framework, trying to understand what the transition looks like. Some of them, for most of them, it's not really clear, which is why I decided to further pursue this project idea. But none of them explicitly report it, explicitly analyze its dynamics. The results are not reported as specific transition emissions, and whether that's something we should be paying attention to, given that they kind of have this unique thing for a few reasons. I mean, the transition is unique because this is really a project that we're just embarking on, and that we kind of have a lot of control over in a lot of ways, as opposed to the global fossil fuel energy system, which has been built over the last 150 years and which is very hard to steer off its current path. So the short answer is it's kind of present in places, but it's really not illuminated in the detail and specificity that is required by the problem.
Great, thank you. moving on, you talked a little bit about uncertainty, but there was a question about, given that you were using different models that have different levels of sensitivity and uncertainty associated with them, and now you're combining all these model results, yet your scenarios were, 1, 2, 3, and there were bars. There were no error bars on the results. And I guess this question was really just, how do you communicate the uncertainty of implicit in this type of a calculation?
Right. So, there's kind of it's a very good point. There are many values and estimates going into producing these estimates, and each of them has their associated uncertainty. I would conceptualize them in 4 ways, one of which I've directly kind of assessed here, which is just the pace of the transition and the amount of emissions that come and warming that comes, and then the adaptation that's required. You're right to point out that the geophysical uncertainty, which is another of these kinds of uncertainties, is not represented here. So in each of these scenarios, there's an amount of sea level rise that's driving that retreat and protection. And I take the median. I'm only working with the median, but probably people in the audience are well aware there's huge uncertainty ranges on sea level rise related to ice sheet stability or instability, as well as other processes. So that's definitely something that should be looked into more. My intuition is that it wouldn't change the overall picture that in our estimates, coastal retreat and protection make up a relatively small share of the global, the total transition emissions. And I think you can see that here, where this 1.5 degree driven sea level rise scenario, it does, the emissions do increase in a warmer world, but again, as I was showing here, the change in those emissions are mainly driven by emissions intensity and not so much by the amount. And I think that would be kind of linearly the case as well for a warmer world. So in other words, what I'm trying to say is there is kind of a geophysical uncertainty analog in here, because this is a much warmer world with more CO2, with more sea level rise than this world. So there's the geophysical, there's the scenario, then there's also economic uncertainties, which would be super important for the amount of energy that is demanded per person in the world. Economic growth is the #1 driver of increasing energy use, which is the #1 driver of emissions. And that economic and demographic future is highly uncertain. And again, we're only using a median projection. So totally great point, and definitely worth looking into more. And then, so that was 3 sources of uncertainty, economics, and then kind of life cycle analysis and emissions intensities, which there are pretty big error bars on too.
Yep. So 2 follow-ups on that. So you mentioned, for example, for the adaptation scenarios, you're looking the median sea level rise. Are you, there was a question about like the scale of your analysis. I mean, you did a global analysis, and I think the question was pointing out that local realities sometimes differ. And, you talked about a median. Did you use a median sea level rise for the whole planet, or did you have some kind of local specificity? And then a follow-up is a question that I had actually when you were talking about the assumptions regarding which parts of the world would have this sort of retreat. And I guess, well, let me ask the first question first, because I had another question about the uncertainty that's associated with assumptions about equity, right? About what do we do globally in terms of protection and energy access? So you can start with the first one about the sea level rise and global versus local scale. Let's start there.
Okay, so there are I mean, in principle, this is a global scale analysis. The energy side of things is totally global. There's no national specificity there. And of course, that is concealing a whole bunch of individual national policy futures that are each highly debatable. So definitely worth following up on that. The cooling is also global. actually, it's a bit spatially. So it has in the building energy demand, there are about 12 regions in the world, and they have differing amounts of warming, different kinds of building parameters, and different kinds of cooling energy demand sensitivities to warming. So there's a little bit of spatial aggregation there. I have totally averaged that or summed that globally in this analysis. And then similarly for the coastal retreat and protection, I showed you before the map of how these things are distributed across the global coastline. That is actually with a good amount of spatial detail, but again, I've averaged it, I've summed it up to the global scale. And yeah, I agree that there's a lot of the uncertainties and a lot of the equity considerations and a lot of like the plausibility of the policy futures that are embedded here would relate to that spatial detail. So I think this should go to the.
So on that equity question, so was there an assumption that places, I think you used the term capital intensity, like parts of the coasts that are capitally intensive, high property values, et cetera, would get more coastal protection and less retreat, and vice versa? Was that part of why that map of Africa showed a very different coastline than other parts of the world?
Yeah, let me go to that map. So this is just encoded in the rules of the optimization in that model. So the reason, as far as I can tell, is that the reason that the African coastline gets such little protection is just because in US dollar not even purchasing power parity adjusted dollar capital density along the coastline, it's compared to the cost, the loss value of the capital density on the coastline doesn't merit either adaptation path. So I think that's kind of just an equity problem that's built into the models, and a good reason why we need to be thinking about what kinds of norms and values are encoded in our models, because again, this is not impartial. There's no reason why someone living on the coastline in Africa should have any differing value in terms of their livelihood being disrupted and displaced by sea level rise than someone in the United States. Actually, quite the contrary, I would say it's more important that people on the global coastline in lower capital density places should be able to continue their livelihoods on the shore, because there's such a terrible history of displacement leading to cultural fracturing and just the great sensitivity to livelihood stability in places that have lower capital density. In other words, if you're a digital nomad living in a rich city in the United States, it doesn't really matter where you live, but if your livelihood is dependent on fishing for the last 500 years, then that's a big part of your identity and is your livelihood, period, how you eat, and there's not much other option.
Great, thank you. There were a few questions about the assumptions regarding the energy sources, and in particular, a question about why geothermal was sort of the percentage that it was, and then questions about nuclear and hydro. Do you have anything like, I mean, where do these distributions come from, and why were the distributions what they were?
So the way that these are represented in this energy system model is these are classified and coded up as scale limited renewables. So the way I think about scale limitation for hydro is that there's only so many river basins in the world that have the right slope profile, the right catchment size, the right flow, and the right kind of seasonality of flow to be delivering hydro capacity. And there's a good literature on scale limitations in hydro. Geothermal is also scale limited because there's only so many places in the world where good geothermal resources are cost effective and available. Now, of course, there's assumptions about technology in there, which are not really well explored in this model. But it's really the scale limitation of those that leads to only a very gradual and moderate increase in this transition, with wind and solar providing the bulk. And the reason wind and solar provide the bulk is they're pretty much scale unlimited. There's massive availability of solar resource on the planet and wind resource in the planet way in excess, orders of magnitude more than human energy demands.
Great, thank you. And I sort of a somewhat related question. Energy conservation doesn't seem to show up in this analysis. Is that so, or is there assumption that as you go forward in the future, sort of building standards will improve and efficiency of of fixtures will improve and will be more efficient generally?
Great question. In the cooling modeling, the building cooling modeling, we do have assumptions about increasing efficiency of the building envelope and increasing efficiency of conversion efficiency of energy available to power air conditioning. So those improving efficiencies are there, but they're the same in all three scenarios. So that's not a factor that's affecting this bar that I was showing you before, these gray bars. Now, the increasing energy efficiency is also in the global energy model. And what you might notice here is that the very top of all of these wedges here is showing global primary energy demand, which has been increasing steeply and accelerating rate through the second half of the 20th century. But in our projections here, it plateaus and then stabilizes at a certain level towards the end of the century. And that's an input to the model that we've decided. We've specified 2,000 watts per person of power in the world, which would be kind of on the scale of a low energy demand scenario that's been circulating in the literature, which would correspond to global energy contraction. So the United States is around 6,000 watts per person. Central African Republic is like 1,200. And so this scenario would kind of say, places that are below 2,000 watts can come up to that level, but everyone else needs to work on their efficiency and come down.
Interesting.
Yeah, so that's a great point.
Yep.
I also tested uncertainty. I also tested the sensitivity of emissions estimates for this scenario to laxing that parameter. So you can go up to 4,000 watts per person, for instance, and it doesn't have a huge effect on the numbers in the end.
And in this graphic with the energy decarbonization, energy mix, is that your graphic or is that from what's the source?
Yeah, so this is output from the NetSet model.
Oh, from the model itself.
Yeah.
Got it.
So you'll notice there's a similar figure in the paper on this model, which I can circulate if people want it. But if you search for Skouridis 2016, you'll find it in Environmental Research Letters. So they used a very similar format for their figure, and they actually only examined this scenario in the main of that figure in that paper. But yeah, this is just output from that model.
Got it. There's a question. I'll try to represent it. Are you looking at the various scenarios that you presented imply a certain investment or scale of production for some of these energy sources or some of these adaptation strategies? Have you gone to that extra level to figure out, is that, do they match up with or how do they compare to the paces of investment that you showed in that one graphic?
Which graphic?
So the question is saying, will any of your future research look at the investment rates and scale of production to make the gradual 2-degree scenario possible?
Maybe it's a comparison to the observed 2015 and 2022 data you showed that the question's referring to.
Oh, so this energy model actually does not have any economics in it, which is a big limitation. But it's really a necessary simplification to try to get at a tractable answer here. I will say that this scenario is pretty much in the middle of the pack of 2-degree scenarios from past IPCC assessment reports, and many of those models do include economics and investment dynamics. I'll also say that this 1.5 scenario we've simulated here is steeper than most of the 1.5 degree scenarios in, for instance, the special report on 1.5 from the IPCC. And the reason for that is that we don't have carbon dioxide removal in this. So we need to respect the carbon budget without overshoot, whereas pretty much all of the official special report 1.5 scenarios have carbon dioxide removal. Most of them have, enormous carbon dioxide removal to get back to 1.5 after overshoot. So yeah, there's some consistency and inconsistency. The question of how investments feed into this is really underexplored in this research, and obviously super important, and something I'm really interested in following up on, particularly with growth feedbacks. Like, for instance, if the transition spurs economic growth in countries like Indonesia, which is around 2,000 watts per person, and they have a rapid economic growth pathway with rising per capita energy use, then is this kind of plateauing still feasible, right? And if this is going on in a bunch of other countries in the world feeding the transition, is economic growth really consistent with these scenarios and with a robust and effective transition? I think that's a really important question.
Mm-hmm. Then there's a question about, in this graphic on the right, I assume they're referring to, where you're showing for the gradual transition use of fossil fuels to engender or to build the renewable capacity. Does that, the question as I'm interpreting it is, does that include or require exploration and production of new fossil fuel sources, or would that energy be available given existing capacity?
Good question. I don't know if current reserves, if current developed reserves are where they would fall on this across these scenarios. Certainly 1.5 would involve early retirement of fossil fuels, which again would cause economic chaos, I think. Probably chaos we need to do. I think my intuition is that this would probably require development of new reserves, but I think that's happening anyway. I mean, in the last 2 years, there's been a big investment into developing new reserves and putting new wellheads in, and bringing new fossil fuel resources, especially natural gas, labeled as a transition fuel, which I have skepticism towards, or just in the context of the energy crisis. So, whether or not current global fossil fuel infrastructure is consistent with this scenario, I think in the absence of economic policies and emissions caps, those resources would be developed. The fossil fuel industry has shown itself very willing to develop resources.
Right. I have one more question myself. There are no more questions in the Q&A, but I invite folks who have any lasting questions to post them while I ask this question. So it's interesting, these types of analyses, as I've seen them done in the past, have used life cycle assessment. And I think there's it's very interesting to me because like a life cycle assessment, as I understand it, requires a very detailed bill of materials. And so there's a limitation on the scale. So right, you couldn't do a life cycle assessment on global, on global adaptation would be an extremely difficult project. But that said, what can you say about, assuming you're familiar with life cycle assessment methodologies and how they work and the tools that are used, the level of uncertainty or precision in this approach versus that approach, would you have any sort of comparison of approaches or methodologies that you might want to talk about?
So we do use life cycle assessment under the hood for a few pieces in here. So for the energy side of things, we're just considering embedded energy in renewables and translating that embedded energy times the deployment of those renewables to give a total embedded energy in the transition, and then multiplying that out by emissions intensities. So emissions intensities are kind of a life cycle. Sorry, emissions intensities of the fossil fuels go into that energy. So already those fossil fuel emissions intensities involve like life cycle type analysis. And so, for instance, one place where the level of detail that goes into that is really important is, I'm from Canada, actually Quebec, and out in Alberta, we produce tar sands oil, so synthetic crude that has super high emissions intensity for crude. Whereas Saudi Arabia basically comes out of the ground. It's as a viable resource already, so it has really low upstream emissions from that oil going all the way up to the production chain compared to Alberta's tar sands, which produce a ton of CO2 upstream. And you have to make decisions on how far upstream you go and how far downstream you go in the emissions. And these things vary across the literature, and it's actually kind of exploited by various interest groups to underestimate their emissions. So for instance, a lot of national fossil fuel and mitigation policies only target upstream emissions and ignore all the downstream emissions. So they're just trying to reduce emissions that go into producing fossil fuels, and then say, whoever burns those fossil fuels, that's not the problem of national policy, which for a rich country that's having high historical emissions, it is a big equity problem. As far as life cycle assessment for other things, I mean, it's always a complicated question, and there's always huge error bars because national, not just because of what's the purview of inside the life or falls inside the life cycle analysis, but also just because of regional differences in the emissions intensities and things like that. I will say one data source that I think is pretty much a life cycle type analysis that tries to represent the global economy, and I think is really useful for trying to get at this question of adaptation, emissions uncertainties. So these people use the process-based integrated assessment model, but I think there's a whole complementary data source that we could be using, which is environmentally extended input-output tables. Input-output tables are just basically matrices of material flows between regions and sectors in the global economy. So a giant, Excel spreadsheet of the global economy. And the environmentally extended versions of that tries to assign water use, land use, and emissions to each of those flows between the whole global economy. And I think that actually would be a really life cycle inspired data set that you could use to try to produce a new estimate and tackle this uncertainty.
Very interesting. And when you were saying what you were saying about how LCAs, the question is how far upstream and how far downstream, it made me think of a question I had while you were presenting, which is the assumption here that the renewable fuels, the energy, and the materials associated with adaptation that are needed in different parts of the world would be sourced locally, or is there built into this sort of movement of materials all over the globe to protect all these places and to provide all this renewable energy?
Yeah, good question.
Because that strikes me as that could be a really significant chunk of emissions. In fact, my understanding is that for many construction projects, it's actually the transport of the material itself that's the bulk of the emissions.
Yeah, and running construction equipment, which is mostly powered by diesel. Yeah, I think most of the LCA data that's going into here is assuming relatively local material supply. So I would say that's very much the case for coastal retreat, because this is based on a few studies, and in those studies they assume mostly local supply. And then for coastal protection, the LCA values I'm using are from a very prominent reference on the topic of construction material emissions. It's a reference by Hammond, I think. Get in touch with me if you want it. That I think also neglects global supply chain transport. So yeah, that's missing here.
So this could be a real underestimate. It could be much worse than, maybe that explains part of the discrepancy here, perhaps.
Right. I mean, so far we have, I mean, as far as my my meticulous scouring of literature goes, we have two estimates of the global magnitude of adaptation emissions, one that's 300 times bigger than the other. So
Yeah.
it's really, really uncertain. And that's
Yep.
that transport is part of it.
So last question. Oops, I'm getting some feedback.
You should begin there.
Last question, methane emissions. You mentioned that you only covered CO2 and that part of that, you thought part of that discrepancy in the range might be that second paper looked at CO2 equivalents, which meant they looked at other greenhouse gases. Where do methane emissions, how would you expand this analysis to consider other greenhouse gases?
That's a great question. There are a few other greenhouse gases that are really important. So one that's missing in the energy side of things is that when it comes to natural gas, which is kind of being marketed as a transition fuel, even though again I have my skepticism about that. Methane, natural gas is methane. So there's huge fugitive emissions. There's huge losses of methane from the wellhead to the end user, and those are neglected here. And the way I would imagine, yeah, I mean, I guess that would affect. Well, I'm not sure if the short answer is I'm not sure if they're neglected. I'm not sure how that would affect it. But I guess, if you're displacing something like natural gas, then you would want to account for fugitive emissions there, and that's not a CO2 emission. That's a methane emission in terms of the emissions abated by launching a faster transition or a slower transition. There are also some other greenhouse gases that are quite powerful that are involved in like industrial electrical engineering projects. So I'll mention one, sulfur hexafluoride. I have a colleague who's very interested in this gas. It's a highly insulating gas that's used in switchgear. If you can imagine that our grid will need to go from a large coal power plant or something like that to a bunch of end users and towards a grid that has a highly distributed renewable solar here, some wind there, etc., and needs to have kind of interconnect a lot of grids to compensate for the intermittency of renewable electricity, then we're going to need a lot of switchgear. That is going to involve just many times more switches than just a much more linear grid. And if we're building out these grids with much more switchgear that involves sulfur hexafluoride, that's a problem because sulfur hexafluoride is like one of the most potent greenhouse gases in the world. I think CO2 is 1 unit, nitrous oxide is 200, methane is 20, and sulfur hexafluoride is thousands. So there's a lot of other like really niche industrial greenhouse gases that I think we should be tracking because they might be super prominent and massively expand in the transition, and we want to avoid a kind of ozone layer type situation with emitting new industrial gases that cause massive Earth system problems.
Thanks. I see Radley, you wanted to give your hand raised. Radley, jump in, whatever you want to.
Awesome. Great. Yeah, just fantastic. I know we're kind of winding down. Question, Corey, like if you were going to sort of look at the whole problem of sort of all the ways that society needs to reduce emissions, and I guess maybe, all the ways we need to adapt, what would be sort of the next piece of this question in terms of some new dimensions you didn't look at here that you might analyze? Maybe the criteria are kind of tractability of analysis, or how important a wedge they are in terms of total emissions, or sort of consistency with your framework here. But is there another aspect of maybe greenhouse gas emissions that we need to move away from, or adaptation strategies we need to employ that you kind of wish you studied here or might look at next?
Yeah, good question. So I've mentioned a few economic things that I'm very interested in. Like some of those are what happens to all of the fossil fuel. I mean, fossil fuels are this massive global industry, and yes, they provide us energy, but they also provide returns on investments to investors. And there's not a lot of sympathy for investors, but one of the biggest investors is public sector pension funds, pensions for teachers. And, I think the economic downsides of that really need to be planned for in advance. That's kind of a transition dynamic I'm very interested in, but there's a flip side of it, which is, as I mentioned before, all the economic growth that's going to be spurred by this wave of investment, which has historically led to increasing energy demand and increasing emissions. And, I think we need to be planning for that for a robust transition, both on the downside, the economic risks, but also the economic benefits. As far as the scope of adaptation, we've considered 3 adaptations here. And the reason we focused on those 3 is because we thought that those were the largest scale adaptations. Air conditioning, almost everywhere in the world where people live gets really hot at some point, and that's going to get worse. And then coastal protection, the vast majority of the global coastline is exposed to sea level rise. But there's a few other adaptations that are really interesting to me. There's been increasing attention in the literature to irrigation, which requires energy to pump groundwater. Also has interesting interactions with hydroelectricity if you're using surface water reservoirs for irrigation. And obviously irrigation demand is going to increase as the atmosphere gets drier under warming, if that affects both drying croplands, but also drying surface water resources. That could force a lot of irrigation underground, which would require more pumping, and potentially release of a lot of emissions, especially since the vast majority of these pumps operate on diesel. So I think, irrigation is also interesting because irrigation cools the land surface. So there's many feedbacks from irrigation that I think it makes it a really interesting adaptation to examine, and potential risks and potential benefits there too. I'll leave it at those 2 examples, but yeah, there's lots and lots of stuff to think about here.
Thanks.
Great. So I guess we're gonna sort of wrap it up. Carl has asked 2 sort of provocative questions. Maybe I'll just pitch them to you for for maybe any concluding statement you have. I mean, he's just sort of curious about the politics of all of this, and your thoughts on you did show an optimistic slide that's a change in investment, shifting from renewables, from fossil to renewables. But I don't know if as you've talked about this work or gotten feedback on it, if you want to say anything about the reactions that people are having and the sort of politics of all of this that you might want to mention as you sort of conclude.
Well, I will say, and as I mentioned, I'm Canadian, so I don't really have that much skin in the game in terms of partisan politics. I will say, I think Joe Biden's political messaging on the climate transition has been exactly where it needs to be and where it should have been for already 20 years. This is a blue collar transition. This is a transition for working people that supports the middle class. I think it's gaining a lot of momentum because of that, bipartisan support. Well, not that much, but because it all went through appropriations. But I think that messaging is in the right place, and in terms of investing in American jobs, investing in economic development in Indonesia, that is how we're going to get lots and lots of investment into renewables. And I think the messaging is going in the right direction. There was another question about, is this feasible? I don't think 1.5 is feasible. I think it's important to keep it on the agenda as a counterpoint and as a comparison point and as an analytic tool. But I think it's feasible for us to make 2 degrees, and we have no choice but to do that. And that involves the right kinds of investments from policy, that involves an involved civil society, and that involves us, giving the necessary amount of demonization to the fossil fuel industry that knowingly contributed to this problem for decades and misled the public and owes the public a massive amount of good faith and course correction.
Great. Thanks so much, Corey. This was a really eye-opening presentation, really, really great work. And thanks for sharing it with us and answering the questions. And everybody else, please join us again the beginning of April for our next first Wednesday of every month, our next seminar topic forthcoming. So thanks again, Corey. This was great.
Thanks to you all.
Okay, bye-bye.